In this video, we're going to look at the momentum method for improving the learning speed when doing gradient descent in a neural network. The momentum method can be applied to full batch learning, but it also works for mini batch learning. It's very widely used, and probably the commonest recipe for learning big neural nets is to use stochastic gradient descent with mini batches combined with momentum. I'm going to start with the intuition behind the momentum method. So we think of a ball on the error surface where the location of the ball in the horizontal plane represents the current weight vector. The ball starts off stationary, and so initially it will follow the direction of steepest descent. It'll follow the gradient. But as soon as it's got some velocity, it'll no longer go in the same direction as the gradient. Its momentum will make it keep going in the previous direction. Obviously we want it eventually to get to a low point on the surface, so we want it to lose energy. So we need to introduce a bit of viscosity. That is, we make its velocity die off gently on each update. What the momentum method does is it damps oscillations in directions of high curvature. So if you look at the red starting point, and then look at the green point we get to after 2 steps, they have gradients that are pretty much equal and opposite. As a result, the gradient across the ravine has cancelled out, but the gradient along the ravine has not cancelled out. Along the ravine, we're going to keep building up speed, and so after the momentum method settled down, it'll tend to go along the bottom of the ravine, accumulating velocity as it goes, and if you're lucky, that'll make you go a whole lot faster than if you just did steepest descent. The equations of the momentum method are fairly simple. We say that the velocity vector at time t is just the velocity vector at time t minus 1. Time here is the updates of the weights. So it's the velocity vector that we got after mini batch t minus 1, attenuated a bit, so we multiply by some number like 0.9, which is really viscosity, or it's related to viscosity, but unfortunately I called it momentum, so we now call alpha momentum. And then we add in the effect of the current gradient, which is to make us go downhill by some learning rate times the gradient that we have at time t. And that'll be our new velocity at time t. We then make our weight change at time t equal to the velocity. That velocity can actually be expressed in terms of previous weight changes, as is shown on the slide here, and I'll leave it to you to follow the math. The behaviour of the momentum method is very intuitive. On an error surface that's just a plane, the ball will reach some terminal velocity at which the gain in velocity that comes from the gradient is balanced by the multiplicative attenuation of the velocity due to the momentum term, which is really viscosity. If that momentum term is close to 1, then it'll be going down much faster than a simple gradient descent method would. So the terminal velocity, the velocity you get at time infinity, is the gradient times the learning rate multiplied by this factor of 1 over 1 minus alpha. So if alpha is 0.99, you'll go 100 times as fast as you would with the learning rate alone. You have to be careful in setting momentum. At the very beginning of learning, if you make the initial random weights quite big, there may be very large gradients. You have a bunch of weights that's completely no good for the task you're doing, and it may be very obvious how to change these weights to make things a lot better. You don't want a big momentum, because you're going to quickly change them to make things better, and then you're going to start on the hard problem of finding out how to get just the right relative values of different weights, so you have sensible feature detectors. So it pays at the beginning of learning to have a small momentum. It's probably better to have 0.5 than 0, because 0.5 will average out some sloshes in obvious ravines. Once the large gradients have disappeared, and you've reached the sort of normal phase of learning, where you're stuck in a ravine and you need to go along the bottom of this ravine without sloshing to and fro sideways, you can smoothly raise the momentum to its final value, or you could raise it in one step, but that might start an oscillation. You might think that, why don't we just use a bigger learning rate? But what you'll discover is that using a small learning rate and a big momentum allows you to get away with an overall learning rate that's much bigger than you could have had if you used learning rate alone with no momentum. If you use a big learning rate by itself, you'll get big divergent oscillations across the ravine. Very recently, Ilya Sutskever has discovered that there's a better type of momentum. The standard momentum method works by first computing the gradient at the current location. It combines that with its stored memory of previous gradients, which is in the velocity of the ball, and then it takes a big jump in the direction of the current gradient combined with previous gradients. So that's its accumulated gradient direction. Ilya Sutskever has found that it works better, in many cases, to use a form of momentum suggested by Nesterov, who was trying to optimize convex functions, where we first make a big jump in the direction of the previous accumulated gradient, and then we measure the gradient where we end up and make a correction. It's very, very similar, and you need a picture to really understand the difference. One way of thinking about what's going on is, in the standard momentum method, you add in the current gradient, and then you gamble on this big jump. In the Nesterov method, you use your previous accumulated gradient, you make the big jump, and then you correct yourself at the place you've got to. So here's the picture, when we first make the jump and then make a correction. Here's a step in the direction of the accumulated gradient. So this depends on the gradient we'd accumulated on our previous iteration. We take that step. We then measure the gradient and go downhill in the direction of the gradient, like that. We then combine that little correction step with the big jump we made to get our new accumulated gradient. We then take that accumulated gradient, we attenuate it by some number, like 0.9 or 0.99, we multiply it by that number, and we now take our next big jump in the direction of that accumulated gradient, like that. Then again, at the place where we end up, we measure the gradient and we go downhill. That corrects any errors we made, and we get our new accumulated gradient. Now if you compare that with the standard momentum method, the standard momentum method starts with an accumulated gradient that's like that initial brown vector, but then it measures the gradient where it is. So it measures the gradient at its current location, and it adds that to the brown vector so that it makes a jump like this big blue vector. That's just the brown vector plus the current gradient. It turns out, if you're going to gamble, it's much better to gamble and then make a correction than to make a correction and then gamble.